So most of you are quite familiar with Goldfeld-Quandt test. It is test of homoscedasticity, heteroscedasticity. In the null hypothesis, we are keeping homoscedasticity, and then we will put heteroscedasticity in the alternative hypothesis, following the standard rule, no parameter type hypothesis in the null position and the other variety in the alternative position. And here also we will check a relationship between sigma I square, and if there is any relationship between sigma I square and the explanatory variable. As I mentioned in the last class, starting from the graphical part, actually we start to check the relation between either RSS and XI or sigma square and XI. Okay, so in case of heteroscedasticity, generally we do that. We bring XI and RSS, XI and sigma I square in the scenario. Okay, so while we will go for Goldfeld-Quandt test, again we will bring this variety, we will bring explanatory variable, we will consider sigma I square, etc. So though you will get the slide in this format, I am putting the matters in a bit different way. Maybe it will be easier to understand for you. So please give heading Goldfeld-Quandt test. It is a small sample or finite sample test. So to begin with, I am mentioning that it is a small sample or a finite sample test. Suppose it is known that sigma I square varies with jth explanatory variable. Suppose it is known that sigma I square varies with jth explanatory variable. Now, if you look at the slide, it is written that it is popular to assume sigma I square is positively related to one of the covariates. For example, sigma I square is equal to sigma square here x2i square in a 3 covariates model. So if there is x2i, x3i, so suppose we are considering this kind of relationship. In the write-up, I am keeping it general. Suppose it is known that sigma I square varies with jth explanatory variable. Let's assume sigma I square is positively related to xij, positively related to xij. Then the test procedure is as follows. Number 1, reorder the observations in the increasing sequence of xij. So, for example, in the slide, if I consider x2i as the variable concerned, in that case, we will organize the data following the values of x2i. Okay. So reorder the observations in the increasing order of xij. Second step 2, omit C central observations. Omit within inverted comma C central observations, C number of central observations. So first I am fixing a particular covariate Xij and then arranging the observations in an increasing order of Xij, and I am omitting C central observations from that order, for the total number of, from the total number of observations on Xij. We are omitting C central observations from total observations on Xij. Fit number 3, fit separate regression by OLS, fit separate regression by OLS to the first and last n minus C by 2 observations, provided of course that n minus C by 2, provided of course that n minus C by 2 exceeds the number of parameters to be estimated, exceeds the number of parameters to be estimated. So what we are doing, we are starting with n observations, on say Xij, putting it in increasing order of Xij. So the observations are like this, and from this we are eliminating C central observations. So total observations now we have in our hand for Xij, that is n minus C. Now I'm considering these above values a group and these below values as another group. So what I'm doing, I'm considering n minus C by 2 number of observations in each group and running separate regressions on each of these n minus C by 2 observations. Okay, so omitting C central observations, we have n minus C, then I'm breaking it into two groups, n minus C by 2, n minus C by 2, and running two separate regressions. Next, let RSS1 and RSS2, let RSS1 and RSS2 denote the residual sum of squares from the two regressions. Two regressions. Let RSS1 and RSS2 denote the residual sum of squares from the two regression equations. With subscript 1 denoting that from the smaller Xij values and 2 that from the larger Xij values. Subscript 1 denoting that from smaller Xij values and 2 that from the larger Xij values. So what I am doing, two separate regression when we are running, and generating two RSS1. Remember that here the observations have been presented in increasing order. So, these group are smaller, giving you the smaller values of Xij. And this set is based on larger values of Xij. Okay? Even, you are deleting C central observations and calculating RSS1 and RSS2 from two distinguished groups, one having smaller values, one having larger values. Even then, if you find that the ratio of two RSS values, RSS2 by RSS1 is very close to 1, in that case, there is homoscedasticity. Because when you are considering two different groups, because one is based on large values, one is based on small values, so two distinguished groups, and if you find that this value is not statistically significantly different, this ratio, in that case there is homoscedasticity. However, if the ratios are different, or it gives us the f value by which we will be able to reject H naught, in that case there is heteroscedasticity. So this is the idea. To RSS we will calculate and fit F statistic on the basis of two RSS. Actually, when we are talking about RSS, we are basically talking about SU square. So actually we are talking about ratio of variances, So in the numerator, there will be a ratio of variance, population to sample in the denominator. That's so. So whenever you will take the ratio of RSS values, actually you are talking about F statistic, because you have the ratio of two chi-square distributions. So what I said, let RSS1 and RSS2 denote the residual sum of squares from the two regressions, with the subscript 1 denoting that from the smaller Xij values and 2 that from the larger Xij values. Then next write down, then set F is equal to RSS2 by RSS1. Step 5. This RSS2 by RSS1 follows if with degrees of freedom in this can be also written as if with degrees of freedom n minus c minus 2k by 2, n minus c minus 2k by 2. 6. Step 6. Reject H naught. Reject H naught if and only if estimated F value, if and only if, is greater than critical value of F So this you are getting from the table. So this critical value you are getting from the table. So if your estimated F value is greater than the tabular value, in that case, you have to reject H naught. Next, it is not a step. These are all the steps. Next, we will say something about the limitation of these Goldfeld quant tests. Otherwise, it is neat, It's a very clear test. We are making two distinguished groups and considering RSS of these two groups and trying to frame one F statistic. If this estimated F is greater than the tabular F, there is heteroscedasticity. Otherwise, there is homoscedasticity. Test is very neat and very popular. However, the main problem of this particular test is how we will count for C central observations. Suppose you have 100 observations, So when you are dropping C central observations, you may drop 20 central observations. I may drop 25 central observations, okay? So while the question of subjectivity is coming, you have to drop several central observations, So different researchers will consider a group of different number of observations, and that will result in different values of F, and on the basis of that, your conclusion may be different. Okay? So this is the most important limitation of this particular test. This is number one. And another thing I mentioned, when you will consider n minus c by 2, this n minus c by 2 should be greater than k. Because when we are taking the degrees of freedom, we are writing the value as n minus c by 2 minus k. So the n minus c by 2 part, that should be greater than number of parameters. So that is one other aspect. So what is the degrees of freedom in your equation? What is the degrees of freedom in my equation? If C central observations are very large, in that case, I hope you are understanding degrees of freedom is falling. Okay, the gap between n minus c by 2 and k, that will fall if the number of central observations are very large. On the other hand, if the central observations are very limited, if you consider a very small number of central observations to maintain the degrees of freedom, etc., in that case, the two groups will not be very different at all. So the entire ideology of test, which is based on we will consider two distinguished groups to run to separate regression, that will be questioned. Okay. So these are the problems with this kind of Goldfeld quant test. So please note down, the power of the test will depend, the power of the test will depend, among other things, the power of the test will depend, among other things, on the number of central observations excluded. On the number of central observations excluded. And will clearly be small, that is power will be clearly be small if C is too large. Power will be clearly be small if C is too large. Within bracket, so that RSS1 and RSS2 have very few degrees of freedom. So that RSS1 and RSS2 have very few degrees of freedom. Or too small. Or too small within bracket. So any possible contrast between RSS1 and RSS2 is reduced. or too small within bracket. So any possible contrast between RSS1 and RSS2 is reduced. So this is all about Goldfeld-Quant test. Here also you will get the view of the Goldfeld-Quant test, the same thing, just, the matter I told you that is more elaborate compared to this. Any question regarding the Goldfeld-Quant test? Anyone, any question? Another important test is Bushpagan-Godfrey test in case of heteroscedasticity, Bushpagan test, and later edited by or modified a little bit by Godfrey. So here also you are finding that we are considering a standard regression model, yi is equal to beta 1 plus beta 2 x2i plus up to beta k xki plus ui, the standard regression model. Then I'm considering sigma I square as a function of different values of zi's, where zi's are known variables and can be xi as well. So it can be explanatory variables of the model or some known variables. Okay, so sigma I square is known up to zi, where zi are some series of known variables, or it can be xi's itself. If there is no heteroscedasticity, that is homoscedasticity, in that case, all this alpha 2 to alpha m in the sigma I square equation will be equal to 0, and sigma I square will be the constant alpha 1 of this model, which indicates homoscedasticity. So if there is homoscedasticity, if null hypothesis is accepted, in that case, sigma I square is equal to alpha 1, or we will get the z values, or sorry, these alpha 2 to alpha m values are statistically insignificant. So how we will do this test? Step 1, derive sig u1 hat to un hat. That is, again, I'm talking about finding the residual values. This ui hat is nothing but ei, that is the residual of the model. Then derive a particular value which we are calling sigma tilde square, which is summation of ui hat square, which means RSS by n. Therefore, I'm giving it the notation in terms of sigma. We know SU square is equal to RSS by n minus k. Here, we are considering sigma tilde square, a kind of sample variance, which is equal to RSS by n. Construct variable pi, which is equal to RSS by this sigma tilde square. Not RSS, sorry, SU square. UI hat square, sorry, UI hat square divided by sigma tilde square. So I am considering the square of the residual divided by these values, this sigma tilde square. After that, I'll regress pi on z2i to zmi. So z2i to zmi, these values are known, or you can consider the explanatory variables x2i to xki. You can consider anything. Either another set of known variables will be with you, or another set of observations will be with you, or you can consider these explanatory variables directly. Once we run this regression, on the basis of this regression, we will consider ESS by 2. On the basis of this regression, we will consider ESS by 2, not RSS, ESS by 2. ESS by 2 will follow chi-square with m minus 1 degrees of freedom. If there are k number of parameters, it will be k minus 1. If you consider the same set of X, in that case, it will be K minus 1. If you consider a subset, in that case, it will be, the degrees of freedom given by number of parameters to be estimated minus 1. If you find your estimated value is greater than that of the critical value of the chi-square at the same degrees of freedom, you have to discard the null hypothesis. You have to reject the null hypothesis, and that will indicate the evidence of heteroscedasticity. Okay, so in the class, first we started with this kind of graphical presentation where we are plotting RSS against Xi. After that, we went for formal tests. We started with the White's test. It is also a popular test where we are considering the residual, square of the residual rather, and that we are regressing on these values, their squares, their cross products, etc. Then the second thing is Goldfeld-Quandt test, where we are considering sigma I square is varying with one of the explanatory variable xij, and now the steps. And the third variety is the Bruchbergen-Godfrey test, where we are starting with the same kind of regression model, and then we are fitting another regression with respect to sigma I square. Then we are calculating sigma tilde square. However, you will look at the matter, everything is based on residual or square of residual, etc. So again, a relation between residual or square of residual and the set of explanatory variables. However, it is not necessary that you will have the same variables here and here. You may consider a subset of these variables, or you may consider another set of variables. However, these variables should be known to you. So this is all about heteroscedasticity. Do anyone have any question? During the exam, if the numerical values are given, somebody asked me whether only the theory is there or numerical exercises are there. Both theory and numerical exercise are expected. If you know how to estimate the parameters of a multiple regression model, if you know how to calculate the RSS, all of you will be able to find out the required value of F or required value of chi-square, whatever we are considering for a particular test. And once you get this value, you have to compare it with the tabular value, and you will be able to understand whether there is heteroscedasticity or not. Okay, so for all these problems, expect both the theory as well as the solution, kind of thing. Okay. So here you will be told that how many observations you need to delete. Okay, so all information will be there. Okay, or information on two regression equations you will have. Two regression equation based on n minus c minus 2k by 2. And from those information, you need to calculate the RSS value, and finally you need to set your F. So this kind of problem you may expect. Here also, the information will be such so that you can calculate this ESS value. Okay, once you get this ESS value, you will be able to compare it with the tabular value, and you will be able to conclude whether there is heteroscedasticity or not. Anyone, any question? Rituja?
No, ma'am.
Okay, Shreya? Rudra?
No, ma'am.
No, ma'am.
Very good. So in that case, I'm shifting for autocorrelation. For autocorrelation, we will follow the same route, introduce the problem. After that, how to what are the consequences of autocorrelation, what is the remedy, how we can detect autocorrelation. So all these issues will be there. Okay. So I'm moving for autocorrelation is also known as serial correlation. So we can call it serial correlations as well. Okay, so there are two sources of serial correlation or autocorrelation. If your error follows a particular pathway, it breaks the classical assumption and follows a particular pathway. In that case, there is pure serial correlation. Now, what is that particular pathway? It can be autoregressive process, AR process. It can be moving average process. It can be ARMA process, or it can be ARIMA process. So what I'm telling, UT is not following it is following a pattern. These patterns, possible patterns are AR, autoregressive process, moving average, ARMA, autoregressive moving average, or ARIMA. Autoregressive integrated moving average. Okay, so all these processes are there. We will start with AR process and just a minute. We will consider AR1. First order autoregressive process we will consider. Okay, that is UT is a function of UT minus 1. In the autoregressive process, U is a function of another U. Therefore, it is autoregressive. Regression on the same variable, However, the order is different. Now, if you consider UT minus 1, UT minus 2, in that case, it is AR2. If you consider UT minus 1, T minus 2, T minus 3, that is the AR3 process. However, we will start with the simplest version, AR1 process. Moving average process is a different type of process. It is a process of epsilon, where all epsilon are classical in nature. However, we consider a series of epsilon. Now, when we will proceed, we will check what is the structure of epsilon. If I integrate AR process with MA process, we will get ARMA. And ARIMA process is a bit different from ARMA. It is autoregressive integrated moving average. Here simply, we will consider the AR plus MA. However, ARIMA is a bit different. In the next semester, when you will start learning about time series, we will learn more about these different series. We will consider AR1 and a standard MA process. So, in this semester, while discussing autocorrelation, we will concentrate on these values. Yes, somebody had some question. What is the question?
ম্যাম আমি আরেকবার নামগুলো বলতে পারছি না।
Autoregressive moving average. Autoregressive moving average is ARMA. ARIMA is autoregressive integrated moving average. Okay, so in case of pure serial correlation, we will consider any form of these things. However, as I mentioned, I'll consider the simplest version, first order AR process we will consider. So pure serial correlation occurs when classical assumption, which assumes uncorrelated observations of the error term, is violated. The most commonly assumed kind of serial correlation is the first order serial correlation. First order AR process, that is the commonly assumed process, in which current value of error term is a function of the previous value of the error term. Ut is equal to rho ut minus 1. So it is a function of ut minus 1 plus a random component plus epsilon t, where epsilon is a classical error. Epsilon is a classical error, classical component. It will follow all the properties of classical error. The magnitude of rho indicates the strength of the serial correlation. If rho is 0, there is no serial correlation at all. In that case, your ut is epsilon t. So there is no serial correlation at all. The mod value of rho is assumed to be less than 1. Since otherwise, remote past would have more influence on recent past, and variance would explode to infinity. Okay, so we need to clarify these two lines. Remote past would have more influence on recent past, and variance would explode to infinity. Within a minute, we will present the AR1 process as an infinite MA process. You will find that actually when we increase the order, you are getting the values rho, rho square, rho cube, etc. That is, t minus 1 will be associated with rho, t minus 2 will be associated with rho square, t minus 3 will be associated with rho cube, etc. So if mod rho is greater than 1, that means later orders are putting more influence on the present value. In the left hand side, you have present value. So this is not desirable. Generally, recent past should have more influence on UT, So, if you consider the world economy at this moment, so the fresh or most important impact is impact of lockdown. Okay, so if we consider this impact should be lesser, what happened before 20 years, that will be more important to assess the present economy. There will be some error in it, because there should be ups and downs, the cyclical movement of most of the variables, and we consider, or we generally smooth all these factors and consider an average trend. Okay, so recent past should have more impact on UT compared to the remote past, and for that matter, we are considering mod rho to be less than 1. To understand variance would explode to infinity, formally we need to calculate it. We will also do that thing in our due course, and you will find, or I think that next, the second point will be cleared. The sign of rho indicates the nature of serial correlation in an equation. Serial correlation may be positive or serial correlation may be negative. Now, what is the meaning of positive serial correlation? This implies error term tends to have the same sign from one time period to the next. If this happens, we call it a positive serial correlation. Now, if in the first period you have the positive value, in the second period you have the negative value, in that case, there is negative correlation. This implies error term has tendency to switch signs from negative to positive and back again in consecutive observations. If this happens, we call it negative serial correlation. Let's check this thing with the help of these diagrams. Here, if you look at the observations, if you consider two observations sequentially two observations, you will find they are moving to the same direction. Sequentially, the observations are moving to the same direction, then coming at a point, they are turning to other direction. However, subsequent observations are following similar nature. Okay, so if this kind of things happen, we call it positive serial correlation. Here also, when we are considering this kind of cycle, you are getting continuously a rising thing, then falling, then again rising, then falling, So if you consider a short period, subsequent observations, they are moving in the same direction. So here also, we are getting positive serial correlation. Now here there is no pattern, no pattern. We are not understanding what is happening actually. So this is giving us no serial correlation. So if I plot the error against time and if we get this kind of diagram, that indicates the error is classical error. The error is not at all serially correlated. This is an example of negative correlation. Here this is observation 1 minus, this is observation 1 which lies in the positive quadrant. Observation 3, negative quadrant. Observation 4, positive quadrant. So if you consider shorter run, if you consider the subsequent observations, you are finding that their sign is changing. So this is an evidence of negative serial correlation. Okay, this is also negative serial correlation. First observation, second observation, third, fourth, fifth, sixth, So direction is changing. So far I talked about pure serial correlation. That is, the source of correlation is coming from the nature of the error term. There can be other sources of serial correlation. For example, omitted variable, incorrect functional specification. All of you are familiar with these two terms, omitted variable bias or omitted variable regression with important omitted variable or regression with incorrect functional form. And in your practical class, you learned how to detect whether there is any omitted variable or not using the OV test. And you also know how to test whether your presentation of the model is incorrect or not. At least to some extent, you now know how to detect all these things. Okay, so omitted variable and incorrect functional form, these two can also work as source of autocorrelation. In case of the first variety, suppose you are not considering any lagged variable, and that lagged variable will be there in the error term and will create a noise. In case of incorrect functional form, the entire specification is wrong. Okay, there is serial correlation. You specified the model wrongly, and naturally there will be the problem of autocorrelation. Okay, so look at the points, look at the points in the slide, you will understand how, the omitted variable as well as improper specification can work as sources of autocorrelation. Okay, so you will get, here you are getting the issues related to omitted variables. And here you will get the specification problem. You are considering a specification YT. A true specification is basically YT is equal to beta naught plus beta 1. There is a type of beta 1 x1t plus beta 2 x1t square plus epsilon t. But instead of linear instead you considered this kind of linear model, okay, and these new error may follow a particular pattern, and that pattern may be autoregressive pattern, and in that case there will be autocorrelation in the model. If you run the test for autocorrelation, you will find autocorrelation in the model. Okay, so check all these things. The next is consequences of serial correlation. If there is autocorrelation, what will happen? The analysis is very similar to that of heteroscedasticity. The steps will be different. However, the mechanism or analysis is very similar to that of heteroscedasticity. In presence of autocorrelation, you will still find unbiased estimators. However, they will not be best. So the efficiency property or minimum variance property, that will be lost in presence of autocorrelation. That will be disturbed in presence of autocorrelation. Estimated values of the parameters will be unbiased. However, they will not the blue estimators, because the minimum variance property or the efficiency property, that is disturbed. Okay, so let's see the steps, how we will do that, how we will get the unbiased estimates, and how we will find that the blue property, the best property, has been disturbed. The existence of serial correlation in the error term of an equation violates classical assumption of non-autocorrelation, and the estimation of the equation with OLS has at least 3 consequences. Pure serial correlation does not cause bias in the coefficient estimates. So coefficient estimates will be still unbiased. Why I mention pure? Because for other sources, omitted variable and misspecification, they themselves generate bias in the estimation process. You are familiar with the omitted variable bias. You are familiar with the bias in presence of misspecification. Okay. So if you consider those two sources, in that cases, there will be bias in the estimators. However, the source is not autocorrelation. Source is either the omitted variable itself or misspecification itself. Serial correlation causes OLS no longer to be the minimum variance estimator. Serial correlation causes the OLS estimates of the standard errors to be biased, leading to unreliable hypothesis testing. Your T statistics are based on estimated value of the coefficient divided by their standard errors. So if the standard errors are not following the best property, in that case, all the T statistics you will calculate, these will be erroneous. Now to understand, you can generate unbiased estimators. However, the estimators are not best. Let's follow several steps. We are starting with AR1 process. As I mentioned, I'm considering here the error is following a particular specification. That particular specification is AR1 process, autoregressive of order 1. So ut is equal to rho ut minus 1 plus epsilon t, where epsilon is classical in nature. Now you can write the similar model in terms of ut minus 1. So ut minus 1 is equal to rho ut minus 2 plus epsilon t minus 1. I'm repeating, ut minus 1 is equal to rho ut minus 2 plus epsilon t minus 1. So in place of ut minus 1, we can plug rho ut minus 2 plus epsilon t minus 1. Now if I rewrite this equation, it can be presented as epsilon t, this epsilon t, plus rho epsilon t minus 1 plus rho square ut minus 2. Ut minus 2 again can be replaced by rho ut minus 3 plus epsilon t minus 2. So in place of ut minus 2, I can present this. Okay. Then in the similar fashion, I can go on and on. And finally, I'll stop when I'll consider epsilon t minus t or ut minus t, that is u0. So the process can be presented using the polynomial epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus rho cube epsilon t minus 3 and so on plus rho to the power t epsilon 0. This is a sum of GP series, rho square, rho cube up to rho to the power t. This polynomial can be presented as summation j is equal to 0 to infinity rho to the power j epsilon t minus j. This particular process, that is epsilon t plus rho epsilon t minus 2 plus rho square epsilon t minus 2 plus rho to the power t epsilon 0, is called the moving average process. So this is the infinite, j is equal to 0 to infinity. So infinite moving average scheme. So AR1 process is equivalent to MA infinity. So finite AR scheme is equivalent to infinite MA scheme. Now, if you look at this MA scheme, you will get the idea why we consider mod rho to be less than 1. Otherwise, t minus 2 will be more important compared to t minus 1. And the period from when we started, the historical period, that period will become the most important period. And therefore, actually, it is rational to consider mod rho to be less than 1. Now, tell me whether everyone is understanding AR1 process is equivalent to MA infinity process. Actually, we need to convert AR1 process to MA infinity process to understand the consequences of serial correlation. With the MA process, the advantage is all these errors, epsilon t, t minus 1, t minus 2, etc. are classical error. Though it is a big polynomial, a big series, However, this series has an advantage compared to AR1 process. The advantage of this series is all the errors we are considering in the sequence are classical in nature. So it will be helpful for us to find out several derivation or solve several issues. Therefore, we convert AR1 process to MA infinity process. In the next step, we will look at the properties of the error term. We will try to find out what is the value of expectation of UT, what is the value of variance of UT. Expectation of UT is equal to 0. As I mentioned, all this epsilon is classical in nature. So if you consider expectation of UT, it will be expectation of epsilon t plus rho, expectation of epsilon t minus 1 plus rho squared, expectation epsilon t minus 2 and so on, plus rho to the power t, expectation epsilon 0. Okay, so this will be the matter. And all of you know that expectation of the classical error should be equal to 0. So expectation of UT is also equal to 0. Next, we need to calculate variance of UT. Now, if we look at this formula, it is UT is equal to summation j is equal to 0 to infinity rho to the power j epsilon t minus j. So variance of UT is basically var of this entire matter, okay? So if I consider var of the entire matter, all these terms will come in form of squares, and we will calculate var of epsilon t minus j. Now var of epsilon t minus j, that is a constant following the properties of classical error. Epsilon is a classical error. So if you consider variance of epsilon t minus j, that will be a constant. So we will get sigma epsilon square. So that I'm keeping outside the range of the sum. And as I mentioned, when we calculate the variance, all the constant terms appear with square, because it is like a plus b whole square kind of thing. Okay, so I'm writing it as summation j is equal to 0 to infinity rho to the power 2j. Now when j is equal to 0, it is 1. When j is equal to 1, there is a mistake. Okay, there is a mistake. This row will be not here. Okay, so please cancel down this row. Please note down this expression where ut is equal to sigma square epsilon summation j is equal to 0 to infinity rho to the power 2j. That will be sigma epsilon square into 1 plus rho square plus rho to the power 4, etc. This rho term will be not there. Okay, so I'm repeating sigma epsilon square into 1 plus rho square plus rho to the power 4, etc. So you are getting a GP series. So this can be presented as sigma epsilon square into 1 by 1 minus rho square. Now rho is a mathematical constant. The value will be something less than 1. So it is a constant. Okay, it is a constant. Okay, so the value of the variance is sigma u square. So variance of ut is equal to sigma u square. So when we are considering this kind of MA process, infinite MA process or AR1 process, we are finding that there is no heteroscedasticity in the structure. There is homoscedasticity in the structure. Next, we consider COV UT US, where both T and S are running from 1 to say small t. However, T not equal to S. So we are calculating this. To calculate COV UT US, I am writing the infinite MA process both for UT and US. So for UT, the infinite MA process is given by epsilon t plus rho epsilon t minus 1 plus rho square epsilon t minus 2 plus up to rho to the power t minus s epsilon t minus t minus s. Then I'm spreading it using the sum values of s, so that when I write the S series, I'll be able to check whether there is any square term in it or not. Another term I am writing in terms of S, that is rho to the power t minus within bracket s minus 1, which is rho to the power t minus s plus 1 into epsilon t minus s plus 1. Actually, t minus within bracket s minus 1 plus dot dot, because it is infinite MA series and will move for quite a long period. I'm also writing the MA process of US, epsilon s plus rho epsilon s minus 1 plus rho square epsilon s minus 2, etc. Now, if you take care of these terms, if you consider t minus t plus s, that is, this kind of term, epsilon s. If you consider t minus t plus s minus 1. So basically you are getting epsilon s minus 1. So while you are writing the T series and S series, there will be several epsilon terms which are common to both the series. So let's see how we will proceed. So when we are considering this, as I mentioned, there will be several terms where there is similar terms. These will give you the variances rather than covariances. So as long as we are considering cov epsilon t, epsilon s, cov epsilon t, epsilon s minus 1, all these values are equal to 0 because epsilon are following the classical properties. However, when the two terms are same, epsilon s, epsilon s, epsilon s minus 1, epsilon s minus 1, epsilon s minus 2, epsilon s minus 2. In that case, actually, you are considering two similar terms. So covariance reduces to variance. Just I proved here there is homoscedasticity. So when I am getting the variance terms, I am writing the notations at sigma epsilon square. So rho to the power t minus s, first time here it is appearing because here the term is epsilon s. So rho to the power t minus s, when I am considering cov between epsilon s and epsilon s, this is variance of epsilon which is given by sigma epsilon square. Then what we are getting, rho into this rho t minus s plus 1. Okay, here you are getting epsilon s minus 1 and here epsilon s minus 1. So rho into rho to the power t minus s plus 1, then variance of epsilon s minus 1, which is sigma square. In the similar fashion, for the common elements between the series, we can generate the variance terms like this. If I take sigma epsilon square rho to the power t minus s common, again I am getting the GP series. So this can be presented as sigma epsilon square rho to the power t minus s divided by 1 minus rho square. Now, sigma epsilon square divided by 1 minus rho square is nothing but the variance value. So I can replace it by sigma u square. So the final value is sigma u square into rho to the power t minus s, which is no way equal to 0. So covariance between the error terms, that is non-zero. So when I am considering AR1 process or MA infinity process, my errors are no longer non-autocorrelated. It is showing the evidence of autocorrelation. So AR1 or MA infinity process generates unbiased error term. It generates homoscedastic error term. However, there is correlation between two error terms. It is non-zero. And this is indicating the presence of non-autocorrelation. Now, with this structure, what is happening to our beta hat? That we need to understand. So, we are coming back to the regression model given by yt is equal to beta xt plus ut, where ut is following a shape, a structure, AR1, ut is equal to rho ut minus 1 plus epsilon t. Now for the standard regression model, beta hat OLS is summation xt yt divided by summation xt square. And by this time, all of us know this is equivalent to beta plus summation xt ut plus summation xt square. We replace yt by beta xt plus ut and we get this. Now one by one, let's check the property of these beta hat. Expectation of beta hat OLS is equal to expectation of beta, which is equal to beta, and summation xt, expectation of ut divided by summation xt square. Already we got that for the AR1 process or MA infinity process, expectation of ut is equal to 0. So the second part will vanish and we can safely argue that beta hat OLS is an unbiased estimator of beta. Next, we calculate the variance covariances of beta hat OLS. Now, variance of beta hat OLS is the expectation of, actually, what is variance value? Expectation of beta hat minus beta whole square. Now, what is beta hat minus beta? Beta hat minus beta is this, summation xt ut divided by summation xt square. So variance of beta hat OLS is equal to expectation of summation xt ut divided by summation xt square of that. Next, we are expanding the series. Actually, in the numerator, we have a1 plus b1 plus c1 whole square of that. That is x1 u1 plus x2 u2 plus x3 u3 up to infinity. The process is going on. Since xt is non-stochastic, denominator we can safely keep outside the range of the sum. So the denominator is 1 by summation xt square whole square of that. For the numerator, we are getting summation xt square expectation of ut square. Actually, we are getting summation xt square ut square and the cross products 2ab, 2bc, we were getting this kind of thing, that is 2 summation xt, xt minus 1, ut, ut minus 1, then xt, xt minus 2, ut, ut minus 2. So in this way we are getting, actually we are considering xt ut, xt minus 1, ut minus 1, xt minus 1, ut minus 1, xt minus 2, ut minus 2. So in this way we are getting the terms. So we are presenting the terms, at the same time we are operating the expectation on the error terms. So as we do so, we already got, if I consider expectation of ut square, what is the thing? What is the value of expectation of ut square?
Sigma epsilon square.
So this is the value of expectation of ut square. Sigma epsilon square. Okay. And how we are getting these 1 by 1 minus rho square? I hope that is clear to all of you. From this series, we calculated this entire thing. Okay. So when we will consider the variance of beta hat OLS, okay, we can use these properties, Variance of ut is equal to a constant sigma epsilon square by 1 minus rho square, which is sigma u square. However, the covariance between the two terms, that is a non-zero thing. So now if we look at this, here there is variance, this expectation of ut square is variance. So I'll be able to replace it by sigma square. However, these cross products will be replaced by sigma square into rho to the power s element, because covariance is, The covariance is sigma square into rho to the power p minus s, this kind of term. Okay, so sigma u square is there both for the variance as well as covariance. So what we can do, this is sigma u square here, here also you have sigma u square. So I'm taking sigma u square common from these terms and I'm left with summation xt square. Here there was rho, so 2 rho into summation xt minus 1. For the second term, when I'm considering the second order, I have rho square. So this series is coming if I take sigma u square common. So if I go on with this term, we are getting this is equivalent to sigma u square divided by summation xt square, square of that. No, sorry, I have taken away. Okay, so sigma u square divided by summation xt square into this kind of term, Okay, here if I divide it by summation xt square, you will get the value 1. For rest of the terms, we are getting this structure. I'm dividing the entire series by summation xt square and multiplying it with summation xt square. Okay, or you can say that one summation xt square I'm keeping here, by another summation xt square I'm dividing the entire thing. And I am getting this presentation, 1 plus 2 rho summation xt minus 1 divided by summation xt square, 2 rho square summation xt minus 2 divided by summation xt square. So it will go on like this. The standard, or in the classical model, the variance of beta hat OLS is given by sigma square divided by summation xi square. And here there is an additional component. I'm repeating, for a classical model, variance of beta hat OLS is sigma square divided by summation xi square. So I'm getting that term and along with that several other terms. So it is very, very clear that variance of beta hat OLS in presence of autocorrelation is no longer the best estimator. You are not getting sigma square by summation xi square. You are getting something else. So it is not the blue best linear unbiased estimator. So beta hat OLS is unbiased. However, the variance of beta hat OLS, that is no longer the variance of the classical beta hat. It is something else. So the blue property of the estimator, that has been destroyed. So this is the consequence of autocorrelation. Any question? Any question on consequence? Any part I need to repeat?
Ma'am, why are we considering the covariance value sigma u square into rho to the power s?
Rho to the power s. Okay. So look at the standard practice. Just look at the thing. I'm coming in a minute. Just check that. If you set, the standard is t minus s is equal to 0. Okay, when I'm considering ut us. Okay, and you can consider t minus s too, no problem in that. But the standard practice is, when we are considering these errors, instead of writing it to be t minus s, I write a single time component rho to the power s when s is not equal to 0.
Okay, ma'am.
Really, you could consider it as S minus T as well. Okay. So some power of rho actually is there. Okay. This is the idea. If you write the presentation as rho to the power S, actually you will get the series in this format, rho square in this format. Otherwise, you can keep it like this, no problem. If you want to write sigma square rho to the power T minus S format, then also there is no problem in it. However, the main thing is the variance of beta hat OLS is not this small one, rather there is a component here. Okay, so if you understand the consequence next, we consider the detection of serial autocorrelation, the most popular method you learned, most of you learned at your undergraduate course is the Durbin-Watson D-test, Durbin-Watson statistic we consider here. So I think most of you are aware of the DW test. Right? You are aware of the DW test or not?
No, ma'am.
Nazma is telling no. In your undergraduate syllabus, you didn't do the DW test? Okay, so if you didn't do, then also there is no issue. So there are two ways to detect autocorrelation. Informal way, in case of heteroscedasticity 2, we mentioned about the graphical method. Graphical method will give you some sense. However, it is not the formal method because at a time you will be able to consider two factors only in the diagram. Okay, and formal method we will learn, that is the Durbin-Watson D-test. So first, let's consider the Durbin-Watson statistic, the formal method, how we will detect autocorrelation using the formal method. Now, to begin with, I'm mentioning some limitation of DW test. In case of first, it is important to note that Durbin-Watson D-test is only applicable if the following three assumptions are met. Number one, the regression model includes an intercept term. If the regression model does not include any intercept term, in that case, you will be not able to do a Durbin-Watson test. However, this limitation is not very, very serious because under most of the circumstances, there should be an intercept term. And from our lessons of omitted variables, etc., we know that it is desirable to keep intercept term in the regression model. Second, the serial correlation is first order in nature. Ut is equal to rho ut minus 1 plus epsilon t. So DW test is applicable if and only if there is first order serial correlation. So this is really a limitation because, you know, when you will handle the real life data, it may happen that ut is not functionally related to ut minus 1. Rather, it is related to, say, ut minus 3. So if this is the position, in that case, you will be not able to apply DW test. That is the problem. Third, the regression model does not include a lagged dependent variable as an independent variable. So if the model is yt is a function of xt and yt minus 1, yt is a function of xt and yt minus 1. Price in the tiered period is a function of several other variables and price of t minus 1th period. If this is the position, you will be not able to apply the DW test. So if your dependent variable appears in the series of independent variable with different lag, you will be not able to apply DW test. So to begin with, we should keep these 3 points in our mind. The model should have intercept term, and when we will consider a specification of the error, you have to specify it as AR1 process. UT is equal to rho UT minus 1 plus epsilon T. And there should not be any YT minus 1 or YT minus 2, etc. The null hypothesis is rho is equal to 0 vis-a-vis rho not equal to 0. Okay. So the null hypothesis is this rho is equal to 0. If this rho is equal to 0, in that case, UT is equivalent to epsilon T. So the error is a classical error. Now, if I write the model as UT is equal to rho UT minus 1 plus epsilon T, this itself looks like a regression model. And the natural estimate of rho hat epsilon T is a classical error. So one can consider this as a ordinary least square model and apply ordinary least square technique to estimate rho hat. So if we apply the OLS technique to apply calculate or estimate rho hat, the value will be summation ut minus 1 divided by summation ut minus 1 square. Okay, summation yt xt divided by summation xt square, that kind of thing. So summation ut minus 1 divided by summation ut minus 1 square. So that can be the natural estimate. Okay. Now, the standard calculation of rho hat is presented as summation ut minus 1 divided by summation ut square. Okay. So instead of considering the lagged value, which we have in the right hand side, the practice is, or Durbin and Watson first present these rho hat where they are keeping ut square in the denominator instead of ut minus 1 square, because it is difficult to interpret the lagged variable in the denominator. Therefore, they are keeping ut square, and they are telling that since first order autoregressive process is equivalent to infinite MSEs, t is tending towards infinity, so it doesn't matter whether we are considering t or t minus 1. However, it will be difficult or it will be impossible to carry the test with these notational construct because u is not observable. So natural substitute of u is e, the residual. So if we move one step further, we should define rho hat as summation ut minus 1 divided by summation et square. Now from our matrix part, already we did all these things. However, we are bringing this element here. We have to incorporate some aspects related to E, because rho hat can be presented only in terms of E. It cannot be presented in terms of U because we don't have any idea about U. U is not observable. Now E is equal to y minus x beta hat. If I put the value of beta hat, it is x prime x inverse x prime y. So what I am doing, I am taking y common and writing this equation to be 1 minus x prime x inverse x prime y common. Beta hat is x prime x inverse x prime y. I have taken y common. This y in the next step I am replacing by x beta plus u. And then I am making this adjustment, x beta, I am multiplying the first two terms with x beta. So x beta minus x prime x inverse x prime x beta. plus, now I am multiplying this term with u, so 1 minus x prime, x inverse x prime into u. From the first part, this x prime x inverse will be adjusted with this x prime x. So you are left with x beta. So it can be presented as x beta minus x beta plus mu, where m is the idempotent matrix given by I minus x prime x inverse x prime. Okay. Since x beta will be cancelled, E is simply M into U. M is the idempotent matrix. The dispersion matrix of E, that is the variance covariance matrix of E, therefore should be given by dispersion matrix of MU. Now, M is the idempotent matrix based on X, which is non-stochastic. So, I can write these as M dispersion of U into M. Whenever you will consider the variance covariance, you need to consider the square term. Generally, what we do, we consider the transpose here. M du M transpose. Now, for the idempotent matrix, M transpose is equal to M. So, you can write M. Again, M square is equal to M. Okay. So, the du, the dispersion matrix of U, that is given by sigma square I. And if I multiply this by M square, which is equal to M, it is becoming sigma square M. So dispersion matrix of E is not sigma square I. Rather, it is sigma square M. So remember that E is autocorrelated even if U is not. U is sigma square I, non-autocorrelated. However, if you replace U by E, that will be always autocorrelated. So E is autocorrelated even if U is not, and thus a test based on statistic rho hat would be erroneous, always showing autocorrelation when it is not actually present. So we have to modify the D statistic. We cannot consider, though E is observable, however, we cannot consider it in this raw form because it will always show autocorrelation. So we may consider summation ET minus 1 whole square, which will be small or positive, small for positive autocorrelation, large for negative autocorrelation, and moderate for no autocorrelation. Okay, so we have to understand this. So we are telling that the standard rho hat defined in terms of E will fail because it will always show autocorrelation. So we need to modify it, and we are bringing the term summation ET minus 1 whole square. Okay, sorry. Okay. Now, is this line clear to all of you? Summation ET minus 1 whole square will be small for positive autocorrelation. Consider the whole square format. It is ET square plus ET minus 1 square minus 2 summation ET minus 1. 2 ET minus 1. Just write down the whole square. ET square okay, and concentrate on this product. if this is positive, in that case, this, this part will be subtracted from this part. If it is negative, in that case, this part will be added with this part. Okay, so that will be bigger. If the value is negative, it will have bigger value. If it is positive, it will have smaller value. Okay, and if this is 0, the value will be moderate, et square plus et minus 1 square. So in between. Okay, so this is the idea. So this summation et minus 1 whole square will be small for positive autocorrelation, large for negative autocorrelation, and moderate for no autocorrelation. Okay, so this is responding to different patterns of autocorrelation. We presented the graph of positive autocorrelation, negative autocorrelation, and no autocorrelation. So what we are finding that this will be able to capture the aspects of positive, negative, as well as no autocorrelation. So the numerator is replaced by summation et minus 1 whole square. Actually, we started with summation et minus 1 divided by summation et square. However, we are modifying the term in this way. We are bringing this whole square, which will be able to capture 3 varieties, presence and absence, and if present, positive or negative, and presenting the thing in this way. Now, as I mentioned, we are considering the time series data here, and if I consider a long series, t and t minus 1 will be very close to each other. Okay, so since summation, okay, one more thing is there. Numerator, for numerator, I have considered the range from 2 to n, because for t is equal to 1, this value will be 0. Okay, and if you consider t is equal to 0, in that case it will be E0 minus E minus 1. Okay, so these are not possible. So we are considering the series from 2, whereas in the denominator we are considering the series from 1. So this is one thing. Another thing is, since summation t is equal to 2 to n et square, that is the first term, and the second term are approximately equal for a large sample. In that case, I can consider this t minus 1 whole square to be et square. Okay, so in the numerator, I am getting 2 summation et square minus 2 summation et minus 1. Now this 2 summation et square, if I adjust with the denominator, I am getting simply 2 minus 2 into, I am getting the rho hat value, summation et minus 1 divided by summation et square. So numerator is 2 summation et square minus 2 summation et minus 1 divided by summation et square. So 2 summation et square divided by summation et square is giving you the value 2, and minus 2 summation et minus 1 divided by summation et square is giving you the value minus 2 into rho hat. Rho hat we defined in that format. Summation et minus 1 divided by summation et square. So D can be presented as 2 into 1 minus rho hat. So on the basis of rho hat, we will be not able to detect whether there is autocorrelation or not. However, if I consider 2 into 1 minus rho hat, I'll be able to detect whether there is autocorrelation or not. This 2 into 1 minus rho hat is called the Durbin-Watson D statistic. The D statistic is given by 2 into 1 minus rho hat. If rho hat is plus 1, if rho hat is plus 1, in that case D is equal to 0. If rho hat is -1, in that case, D is equal to 4. If rho hat is 0, in that case, D is equal to 2. So I am considering two extreme maximum value of the correlation, +1 and -1. For +1, it will be 0, D statistic or David-Watson D statistic will be equal to 0. For -1, it will be equal to 4. And for no autocorrelation, it will be equal to 2. If D is close to 0 or 4, the residuals are highly correlated. And if D is close to 2, in that case, the residuals are not correlated. Is it okay to all of you up to this? How we are finding the DW test statistic D? How we are framing this? How it will capture the essence of autocorrelation? Is it clear? Any question? Statistic D depends on excise and hence no general cutoff points can be obtained. I'm telling that it is if it is close to, however, what is the value? Close to means, a series of values. So what is the cutoff point? When I am telling that it is approaching to 0, what is the cutoff point? When I am telling that it is approaching to 4 or 2, what are the cutoff points? So statistic D depends on excise and hence no general cutoff points can be obtained. How it depends on excise? D is framed with residuals. Residuals are coming from the regression models, So these are residuals are functions of excise. However, two other statistics, DL star and DU star, have been developed such that D is stochastically larger than DL star and smaller than DU star. Okay, so we are, or statisticians or econometricians gave us two cutoff points, DL star, DU star. From these distributions, critical points DL, DU independent of excise can be obtained. So if D is less than DL, positive autocorrelation is present. Our value is D is equal to 0. Okay. So instead of 0, I am bringing a cutoff point DL. Okay. Econometricians are giving us a cutoff point DL. If your estimated D is less than DL, you will treat it as it is approaching towards 0. So positive autocorrelation is present. Alternatively, if D is greater than DU, what we told, if D is equal to 2. However, I mentioned if D approaches towards 2. Now, what is the cutoff point? DU is the cutoff point. So if it is not 2, however, crosses DU value, in that case, there is no autocorrelation. So if it is not 0, however, it is below DL, in that case, there is positive autocorrelation. And if it is not 2, however, if it is below a particular value, in that case, no autocorrelation. So this norm is followed. So using statistical tables, we may test the hypothesis of zero autocorrelation against the hypothesis of first order positive autocorrelation. All of you have the soft copy of Mandala. You will find that at the end, there is table for D. For a particular value of D you are calculating, the table will give you the relevant DL and DU. So if you find D is less than DL, you can argue there is positive autocorrelation. If you find D is greater than DU, you will argue there is no autocorrelation at all. So look at this point, okay? I'm coming 1. Okay, so on the basis of Durbin-Watson test statistic, if you understand those parts, separately for 4, we do not do anything because in between the value 2 is coming. So we check the value 0 and 2, and for higher end, we consider the thing in this way. Okay. So if D value lies in between 4 minus DU and DU, in that case, do not reject H naught. And if D is less than DL, না না, এটা শুধু PG1. D is less than DL, we reject H0. Okay, so for these two, we reject H0, and for these, do not reject H0. And this is very important. If D lies in between DL and DU, do not cross any of the two limits. In that case, the test is inconclusive. This is a serious problem with Durbin-Watson test. If D lies above DU, below DL, you will be able to conclude. However, if this pattern is followed, the test remains inconclusive. Okay, so we can show these things using the number line as well. So here we are considering a number line. Okay, so check, this is 4, this is 0, and you are understanding in between this is the 2 value, this is the value 2. Okay, this range is the range in between DL and DU. So we have a DL which is 1.12 here for this particular problem, and we have the DU value which is 1.66 here. So DL is 1.12, DU is 1.66. So if the Durbin-Watson estimated value is 0.60, in that case, there is positive serial correlation. If it is 1.28, in this range, the test remains inconclusive. However, if it is 1.78, okay, in that case also, you will be able to conclude that no positive serial correlation is there because it is crossing this limit DU. Okay. So look at this example. For every D statistic, you will get DL and DU, and you will be able to, looking at the DL value and DU value, you will understand whether your test is inconclusive or whether you can claim there is positive correlation, negative correlation, etc. So this is the consequence as well as the detection of autocorrelation. Next is the remedial method. In presence of autocorrelation, how we will estimate the parameters of the model, how we will get back our estimated values which are based in nature. So this part I need to discuss tomorrow. Any question up to this? Check the slides, check the table from Madala. It will be better understandable. Do anyone have any question? Anything I need to repeat?